satisfaction. And we'll have a chance for you to participate as well. So I do want to ask you to mute your mics. That will be helpful, unless you're actually, and your computer mics too, that will help. And let you know that this session is being recorded, so be aware of that. And could you move to the next slide for me, Tori? So Tori O'Leary, I will introduce the team. So I think I've already kind of gone through that. So here's the program team. For those of you who have not met the team at the National Institute of Aerospace, that's me, Shelley on the left, and then Stacy Dees is our higher education portfolio manager. Tori O'Leary is a senior program coordinator. Hi, Tori. And Jan Kerbjan is also a senior program coordinator. So this is the team that you can reach out to at any time when you have any kind of concerns or questions. We are here for you. Our whole world revolves around helping to make sure that you have what you need to be able to participate fully in this competition, and anything that we can do to make your experience the best it can be is what we're trying to do to help you all. Next slide, please. Okay, here's our steering committee. So we've got Dallas Binhoff. He's our new chairman this year. He's been a long-standing member of the team. I'm happy to have him from Sislinger Space Development Company, Ken Bokham with Northrop Grumman, John Bradford with Spaceworks Engineering, AC Chenario with Blue Origin, Mel Farabee, formerly with NASA Langley Research Center. He just retired, but he's staying with us, so we're happy about that. Heather Rarick, she's at NASA Johnson Space Center. We have Amanda Ireland with Boeing. She's a former RASC-AL student. That's always fun, and now she's working as in the profession. And we have Chris Jones, same thing. He was a former RASC-AL student and is a civil servant over with the Space Missions Analysis Branch at NASA Langley Research Center. We have Russ Joyner with Aerojet Rocketdyne, and then Pat Troutman, who is the sponsor, the technical monitor and sponsor for this program with the NIA over at NASA Langley Research Center. And he knows an awful lot about the future of human space exploration and human scale architectures and all the different technologies and things that are going into a lot of the planning for NASA's future missions. Next slide, please. Is there anything else? Maybe is that my last slide? Okay, so I think I've already provided the context for our session for today, and now I'm going to turn it over to Pat and let him be able to provide some more context for you all. Just thank you again for your time and your interest in this competition. We're very excited and hope that we'll see you all in, or those of you that make it through, see you in Cocoa Beach in June. It's a ton of fun. And that is really, if that's not motivation enough to do a good job in your submissions, I promise you it's a great time and you'll get a lot out of it. So, all right, turn it over to Pat. Thanks.
So in the spirit.
We can't hear Pat.
Not sick, are you?
Do you want to have your, well, let me see your happy face.
Oh, okay.
All right, let's try
All
this. Right. There we go.
You can see my happy face. Okay, there it is. All right. So sorry. We're Shelley's going to move 60 for me while I talk. How about that? And so we follow all the rules here. So this year at RASC-AL's, our themes are they're spread far and wide as they usually are, but we have a couple focused on missing pieces for the moon. We have this power utility palette. We have the logistics transfer systems. We have sample containment systems. These are, I'll call them smaller elements that we haven't focused on enough on the NASA side. And it's reflected in some of the questions you guys have asked us. What comm rates do we use? What temperature we keep the food at? All sorts of great questions. And I'll tell you right now, those are the same questions that we're asking right now of ourselves. So some of the responses are a little bit sketchy. They say, state your assumptions and tell us why. And that's because we're interested in actually forming what the requirements should be for these systems that will enable people to live and explore on the surface of the moon and on Mars. So just a little preface for why they're a little bit sketchy in some of the responses. We are trying to start the development of a human lander, of logistics systems, of power systems, of habitats, rovers, all at the same time. And so it's quite a complex systems integration problem. So we're going to do a little bit of estimating, a little bit of assumptions, and then we iterate and get it into the right size box. So you're part of that process. We're looking for you to look at the problem from a fresh perspective, give us what you think should be the constraints, the main drivers, and innovation in your design, because it will feed into what we're going to do on the moon and Mars. So I want to thank you all for that. And for the great innovation and excitement you'll bring to the program. And hopefully we'll all see you in Cocoa Beach, and we won't be wearing any of these things next year. Hopefully. Shelly and I had arm wrestle over this year, but it was interesting. Okay, but regardless, next year, hopefully we see you all at Cocoa Beach. Chris, did you have anything to add to my comments?
Honestly, Pat, you covered a lot of it, but I think I'll just kind of build on your points there and say, first of all, it's great to have everybody on the line here. Really appreciate all the questions and looking forward to seeing what you submit. I think you'll see as you flip through the document that Tori sent out that, yes, in a lot of cases, the assumption we gave was describe and justify your assumptions. And the reason for that is that by design, we're looking to see what you can do to solve the kinds of problems that we're facing at NASA every day. We often get these same kinds of problems where they're under constrained, they're under specified, and we can't just, go back and ask for clarification. We have to make our own assumptions, apply our own engineering judgment, and use that to do the best we can with it. And so what I want you to think about as you go forward, putting together your proposals, and for the teams that are selected, going through and doing your full design, is when you come across a question that either in the Q&A we said, describe and justify your assumption, or something else comes along, think about how would you go about answering that. What data could you use from other systems that have been built before to help you answer that question? Has somebody published something somewhere that could give you some ideas? Or can you apply the engineering judgment you've been developing in the course of your education in order to come up with your best solution and then present that to the judges? Because in a lot of cases, there's not some definitive answer we're holding back from you. As Pat said, we're really looking for revolutionary new ideas from you to help us solve these very problems that we're facing. So with that, we'll move on ahead.
Thank you so much, Pat and Chris. We really appreciate your remarks there. Just so everybody knows, now we're going to be moving into covering the questions that we've highlighted in that document that's just been sent out. So if you guys want to follow along with those highlighted questions, that's what we're going to be doing now. Moving on first to the portable utility palette highlighted questions. The first of which, and either Pat or Chris, you can go ahead and answer this. We've got the
Tori, can I interrupt really quickly?
Absolutely.
Before we jump into the questions for each section, Pat and or Chris, would either of you mind giving a few words about the theme, why it was selected, why it was chosen, and kind of what you're hoping to get out of that particular theme?
Sure, I'll do that. Can you hear me? I'm on my phone now.
Perfect, thank you.
Okay, good. So the portable utility palette. So in any situation where you're exploring or you're going off in uncharted areas, it's always nice to have some sort of backup. So think of it, back yesterday, I got a call from my wife at lunchtime. Hey, I was driving this car around. She works in an auto mechanic shop, and she was test driving a customer's car, and it broke down in the middle of nowhere. Can you come give me a jump start? Well, think of the portable utility palette as that jump start capability, not just for pressurized rovers or unpressurized rovers, but for habitats if a string of power goes down. So instead of designing everything on the lunar surface to be multiply redundant to power systems, we have one that can be pulled around like a Honda generator. So the portable utility palette becomes that set of redundancy that we don't have to build into every system, but we build it into one system and we can move it where we need it. Because not every system is going to have multiple redundant failures in their power system all at once. So it's an architectural type thing. The other thing about the portable utility palette is that it's also becomes a range extender, an oasis of energy. The lunar South Pole, where we're talking about using this, has areas of nearly constant sunlight, but also has a lot of areas with lots of shadows. And the further you get away from the pole, the more it goes into a light daylight, a light dark cycle. So if you have this portable utility pallet, which can charge itself and which has a vast reserve of energy on it, you can actually artificially extend this oasis of light out further and be able to explore more. So it's about increasing exploration, it's about decreasing overall system mass across the architecture, and it's about putting in that extra redundancy and risk reduction and that flexibility. Because a third reason for it could be, hey, I have this ISU production plant, and if we could double the production, if we just could double the power, tow it over there, hook it up, and double the power. So that's why we have a portable utility pallet in the architecture.
Thank you so much, Pat, for clarifying that. I think that's going to help a lot of the teams with visualizing the needs that we have for this theme. And I am going to move on now to the first highlighted question that we have. Like I said, Pat and Chris, either one of you, feel free to answer this, but we'll go ahead and start. Can RASC-AL provide any additional technical data on the Lunar Gateway, specifically its communication system? What are the methods of communication for communicating with the Lunar Gateway? Is it only sending or only receiving, or does it need communication both ways? And what actual data is being communicated?
I will yield to Chris.
All right. So yeah, one of the big functions we're looking for here is to use it as a relay to communicate data, especially low bandwidth data and video, from the different surface systems we're going to have. That could be crew out on an EVA, that could be the lunar terrain vehicle, to other surface assets and to orbital assets when they are in view, when they're in line of sight. And we want it to be able to do both transmission or receiving. We're still working on seeing if we can compile some other publicly available resources about Gateway. And once we do that, we'll publish those two to help clarify some of these questions.
Thank you, Chris. So we're moving down to the next one, number 24. Can you explain the 60% discharge and the 125 kilowatt of energy required? The prompt states provide at least 125 kilowatt hours of energy for other systems to draw on at less than 60% depth of charge. As I understand it, both kilowatt hours and depth of charge are metrics of energy. Is there a power requirement for the PUP? Is 125 kilowatts per hour at 65 DoD an end-of-life requirement? And how much does the battery capacity need to be?
Go, Chris, you got them all.
Sure. I'll take them until I get stumped, and then I'll throw them to you, Pat. So yeah, in this case, we're talking about the end-of-life requirements that are going to drive design. So that's the 125 kilowatt hours of storage with a 60% depth of discharge limit. With regards to power requirements, transfer rates, battery capacity, again, those are places where we want you to think about what would be most useful to other systems and use that to help drive your design. The big thing we're looking for is the energy storage requirement.
Thank you, Chris. Moving on to 27, is the PUP intended to constantly service other instrumentation, or is it only used as needed? What other machinery or devices will the PUP be charging? For example, is it charging a habitat, or is it recharging a rover on the moon?
So I'll kind of point you back to the description that Pat gave at the beginning of the theme and say there's a variety of applications it could serve. So we want you to tell us where you think it might provide the greatest benefit given the design of your system as part of your overall description.
Number 35, does the PUP need to be self-mobilized or only moved by the future mobility asset?
So it doesn't need to be able to move itself. So you don't need to try and design a mobility system as part of your overall design.
Is there a standardized electrical connector used for energy transfer? What are the interfaces or connections required to supply lunar assets with power?
Again, as I've answered for a few of these here, this will be one where I recommend you see what you can find out there in the published literature, but also if there's not something immediately obvious, make an assumption and justify it.
Thank you, Chris. And now we've moved on to the Universal Sample Containment System highlighted questions. And if either you or Pat would like to give a kind of a short description of this theme, we would absolutely love that.
Well, Pat, why don't you take this theme and then I'll describe the next theme.
Okay. All right. So we're investing billions of dollars to send people and robots to the moon. Um, but what we don't have is a highway of capability or payload coming back from the moon. We can send lots of rovers, lots of robots to the surface. However, when we get there, we have to bring everything back currently right now through Orion, which is limited to 100 kilograms. Now, that 100 kilograms, of that 100 kilograms, that's not just samples, that is the systems used to hold the samples. So the more efficient and lightweight we get with those containers and systems that bring the samples back, the more samples we have. For example, right now it's typically 50% overhead and 50% sample at best. If you guys are innovative and come up with a way of getting 25% containers, 75% samples, like 75 kilograms on an Orion mission, you've just increased by 50% our return on investment for getting samples back from the moon. Furthermore, if we can take those same containers and we can robotically return them some way, now we have that two-way system of people and robots going to Mars and going to the moon, and people and samples coming back from the moon. So it's important for us to have the most efficient design possible given our current constraints, and that only becomes a multiplier if we find some other way to get cargo back from the surface of the moon, which was, of course, a RASC-AL's topic last year. So it's a logical follow-on is how do we package and deliver this stuff independent of whether it's on Orion or some other thing, but what are the efficiencies we can gain in packaging it together?
All right, thank you so much, Pat. We're going to move on to the questions that we have highlighted for this theme. Starting with number 11, are there any specific data points that must be constantly monitored and displayed during the sample's containment? Does the mission require data storage regarding the temperature of the sample storage device?
So yeah, there's definitely some data we're going to want the system to be able to track, because an important point here is the ability to maintain the right environmental conditions for each kind of sample you're bringing back. So however it is you're dividing up the number of, storage bays or whatever you want to call them, knowing things like temperature, pressure, humidity, the things that are most relevant to ensuring the integrity of those samples, that's data that's going to need to be returned by your system.
Thank you, Chris. And what is the maximum volume and weight of samples to transport? What sample dimensions do we expect to be collected during the mission? Is there minimum or maximum sample size? What is the average size of the samples being contained?
So yeah, in a lot of cases here, we know that we are going to want to take samples, but not yet the specific things we're going to want to take. Frankly, a lot of that we may just learn from the ground truth of being there. So what we want you to do is help design what the system can do, keeping in mind that you've got the constraint of 100 kilograms of total mass for all of the samples you can collect and the mass of the entire system, and that there's going to be a desire to carry a variety of different kinds of samples. So using that, you can tell us what kinds of masses and volumes and types of samples you're able to transport, and that will give us some sense of, okay, how good of a system is this?
All right, thank you, Chris. And I think that is the end of this theme. We're moving on to the Mars-based ISRU architecture highlighted questions. And Chris, I think you are the expert here, if you don't mind giving a short debrief on this theme.
Yeah, this one's a little near and dear to my heart, so I won't read the entirety of my dissertation out loud for it. But one of the things that we have often thought about here is as we transition to bigger and more ambitious missions on Mars, we're going to want to be able to produce really large quantities of propellant from Martian resources. We're getting a better handle on the potential availability of ice or other ways to get access to hydrogen atoms while we're on Mars. There's carbon dioxide in the atmosphere. There's potentially other resources available. And so what we're looking to do here is to understand, what does it take to produce not just small quantities as a technology demonstration, or even enough to fuel, a small two-person ascent vehicle, but down the road, what does it take to provide really large scales of propellant on a consistent year-by-year basis. So what we're trying to do here is ask you to design the entire concept of operations for that. If you were given the knowledge of where to find ice or water somewhere on Mars, what would you do with that, and how would you turn it into 50 tons a year of propellant? We're also giving you the freedom to tell us what propellant you would want to make. In the course of thinking about future missions for Mars, there have been proposals for just pure oxygen and hydrogen, for different kinds of hydrocarbons, sometimes for approaches even more exotic than that. But at whatever propellant combination you choose to make, we want to see what you would do and what kind of systems you need to produce it at a rate of 50 metric tons a year.
Thank you, Chris. And we actually have quite a few highlighted questions in this category, so we'll go ahead and move on to those. Number 6, as indicated in the requirements, the ISRU architecture should operate for long durations, yet no specified amount of time is given. Is there a preferred or recommended amount of time, or should we determine such number based on our design and assumptions? How long is our architecture expected to last and maintain a production rate of 50 tons per year?
So I didn't want to have a really explicit duration here, but so we would like to kind of see your analysis of what kind of system you can deliver and how long it lasts. But personally thinking about it, if we can see at least 5 years of operations, we could be confident that's enough to enable multiple Mars missions, which then increases the likelihood that an ISRU system kind of pays off in the investments you take to producing it. So at the very least, think about it in terms of multiple years in order to feed multiple missions, not just as like a one-shot 50 tons and you're done.
Thank you, Chris. The next question is 8. For the 50 tons per year propellant requirement, should that be viewed as the full demand for this ISRU or as a bare minimum to be exceeded? If we were to produce more than 50 tons of fuel per year, do we assume that that can be added to the next year's production, or does it have to be a standard number of 50 tons per year, no more, no less?
So yeah, the 50 tons is the minimum. It's the floor. If you're able to produce more and store it, you could count that as then being available to meet future years of demand. And we'd also be interested in understanding, if you've got a concept that scales up well to do 75, 100, 200 tons a year, that'd be good to know. If nothing else, it provides additional margin on something that would want to consume the 50.
All right, next question is 9. Is the 50 tons per year being taken out on a reliable basis, meaning we only have to design around a 50-ton maximum for storage, or is it not being taken out? So after 3 years, we would have to store 150 tons. / is the tank capacity for storage supposed to be for 50 tons per year?
So you get to determine the specifics of your storage concept, but assume that there is going to be some other system that is going to pull out 50 tons per year from your storage system. So you might cap it at just 50 tons of storage, or building off of what we talked about in the previous question, you might be accumulating at a greater rate and then having, parts of that spent from time to time to meet that annual demand.
Number 12, the guidelines talk about extracting water from a notional water ice reserve. Do you recommend detailing one or several sites that could potentially have the required amount of water ice? Or should we identify where these reserves will be? Are there any limits on the location of the architecture?
So for this theme, we're actually less focused on finding the right location to do this and more interested in the concept to take advantage of it once such a location is found. So in this case, you can assume the location has been identified and you tell us what it would take to acquire it from some arbitrary location. If the course of your design does have a geographic constraint to it, then we generally prefer to think about Mars landing locations closer to the equator, but it's not going to be a specific constraint, so there's not a penalty for moving further north or south from the equator.
Thank you, Chris. Number 26, what defines human intervention? Does the restriction on human intervention only cover propellant production and storage, or does it also include retrieval of the stored propellant? Are we responsible for automating how propellant gets from storage to humans and vehicles? Is human interaction allowed during, and can astronauts assist with, system deployment and assembly before operations begin?
Okay, so broadly, the restriction on human intervention applies to the big functions or operations that are described in the theme. So that does include the deployment and assembly of the system, as well as its operation to produce and store the propellant, and the maintenance that allows it to stay up and running for multiple years. You don't need to worry about the design of how that propellant would go from your storage system to some client vehicle or other system. So that part can stay out of scope.
Thank you, Chris. Moving on to 27. Can our architecture operate by human telecommunication, or is it supposed to be fully autonomous?
So remote operations by, teleoperation are fine, but keep in mind that there's almost never going to be any human operators remotely nearby, whether that's on the Martian surface or in Mars orbit. They're almost always going to be operating from Earth or Earth's sphere of influence. So to the degree that you're designing for that teleoperated approach, keep in mind the communications lag between Earth and Mars.
Number 33. The theme description states that production should be at a scale of 50 tons per year. In this case, does year refer to Earth years or Martian years?
Yeah, thanks for the question here. So we're looking for Earth years here.
Thank you, Chris. Is there a limit to the surface area real estate that we can take up on the Martian surface?
No, for this concept, if you're looking to, plow up a large field of Mars in order to acquire regolith, that's perfectly reasonable and in scope.
Thank you. And that actually is all of the questions that we have highlighted for this theme. We're going to move on now to the questions we received in advance for the Suitport Logistics Carrier highlighted questions. So this is the SPLC theme. Would you or Pat like to give a brief introduction to this theme?
I'll throw this one back to Pat.
Okay, Suitport Logistics Carrier. So, Suitport is a very important part of that logistics carrier. And so this is where we look at an architecture integrated across multiple elements. So let me explain the Suitport first. The Suitport is a mechanism that we use such that the crew can go in and out of the pressurized rover or the habitat with minimal dust intrusion and minimal pressurization, repressurization. So it saves resources and it saves contamination. That's very important when you're going Mars forward. So that's what we use for when the crew go out on their lunar and Mars walks. Now we thought, well, hey, if that minimizes all that transfer of dust and stuff like that, what's good for the people is good for logistics. So we've come up with a method of operation where these carriers, which are, about the size of a fully suited crew, you fill them full of the logistics, and in 16G, 2 crew could actually pick it up at a contingency. We don't really want them to do that. But we use that same mechanism for getting goods transferred from the lander into either the rover or the habitat. So these carriers come down on a lander. They are positioned either by the crew, by a davit, by a rail system. You can dabble in that. And then they slide onto the back of where the crew member usually goes in with this EVA suit port, but there's a suit port on the side of the logistics carrier. And that allows the crew inside either the rover or the habitat to open up that carrier and pull out what's inside without any of that dust from the outside going back in. And again, minimizing contamination and minimizing the use of precious gases for repressurizing airlocks and things like that. So that's why we have that particular mechanism. On the moon, it saves resources and it saves time. And on Mars, it's very important because it really minimizes the dust transfer. Now, we know when we get to Mars, we probably won't be able to prevent all of it. But if we can prevent 95% of it, that should go a long ways towards hopefully making the crew is healthier and happier and not transferring bugs back and forth from the Earth system to the Mars system. So that's the reason why we have a Suitport logistics carrier. The reason it's sized it is the way it is because it has to work in the same places that the EVA suit works. So it's about the size of a crew member in an EVA suit. Certainly going to be heavier because you got to stuff it full of goods. But there's the rationale for the Suitport logistics carrier in the architecture context.
Thank you so much, Pat. Hopefully that context kind of helps some people put into perspective what the Suitport Logistics Carrier theme is asking for. We actually did receive a lot of questions for this theme, so we're going to go ahead and move on to the highlighted questions now. The first one is number 3. Is the SPLC meant to be mobile?
So Yes, depending on exactly what you mean by the word mobile here. So it needs to be able to be moved from where it comes down on a lander to, as Pat said, being able to interface with a habitat or a rover or something. But it doesn't necessarily have to be able to transport itself. You just would need to understand how it can be moved by a surface rover, or move it itself. It's not a hard requirement that it can move itself.
Thank you, Chris. Number 5. What do you anticipate the distance is from the lander to the habitat? Will the SPLC only be moved and mounted while astronauts are present?
So the distance will be on the order of maybe the ones, maybe slightly over 10 kilometers in order to transport. And at this point here, Pat, do we think it would only move when there's astronauts there, or would we also want it to be able to be moved robotically?
Pat, you're muted.
Shelley was distracting me. What was the question?
Do we think that the SPLC is only going to be moved while there's astronauts on the moon, or do we also want it to be able to be moved robotically?
So that's one of those. Right now, our current plan, which is I don't think is very good, is that the astronauts are going to move it because that wastes their time. We're spending billions of dollars to send them there, and they shouldn't be moving cargo around. They should be exploring and thinking and taking in the awestruck beauty of the lunar surface. So we would love to see concepts that either fully automate or partially automate the transfer of the support logistics carriers to either the rover or the habitat and minimally involve the crew. Now, of course, to transfer the stuff from inside of the carriers to the inside of the habitat, the crew will have to open the hatch, reach through, and pull out, but they have to put it all away anyway. So yes, we would love to see innovative ideas for automating the logistics transfer process.
Thank you, Pat, and thank you, Chris. We're moving on to number 9. Are you saying, I think this question has been answered at this point, are you saying that a single monolithic unit that masses 1,600 kilograms will be picked up and connected to the habitat via a suit port? Are suit ports rated for 1,600 kilograms?
So, Pat, I actually want to throw this back to you again because I think there might still be a little bit of confusion here.
So the landers we're talking about are in the 1,600, 1,800 kilogram class. In our current point of departure concepts, we do not put that all in one carrier. We split it up into 4 more carriers so that in that contingency case, they could actually move it. That's also important when you talk about we have to be able to put this carrier in the same place, as I mentioned before, that a full-size EVA seat would go, because that's the interface that we get it into the rover. So I would not expect to see any designs that were monolithic for 1,600 kilograms of logistics. I would expect to see those carriers being broken down into smaller pieces, even though that's less efficient. But there are benefits to redundancy. If you lost one, you don't lose everything. But again, the big driver there is getting it onto the pressurized rover, and for the habitat, there's actually a hatch that goes through, and we put in the dimensions for that. So I doubt you could design one that met those dimensions that weighed that much fully loaded. So it should be apparent when you look at the numbers that you want to divide it into smaller pieces, and those pieces have to fit through the hatches that we specified.
Thank you, Pat, and thank you, Chris. Much simpler answer there than the extended version. Number 17, the theme states driving dimensions, interfaces, and utility needs will be provided, as well as a breakdown of the type and amount of logistics that need to be accommodated. Descriptions of the surface assets and SPLCs will interface with will also be provided. When you refer to various specifications that will be provided, will they be available prior to the proposal submission or only after a team is selected?
So, in the spirit of this theme and really all of them, we're kind of working on some of these problems in parallel with what you'll be doing. And so as we have answers that we can release to our international partners and release publicly, we're going to try and provide those to you. So we'll probably be updating some of the resources on the RASC-AL website as we go. We did add a few things earlier today in a PDF file that is up there on the website that will give you some additional information there, along with the clarification in the theme that we added on September 1st.
Thank you, Chris. And if you guys go into the Q&A summary document under number 17, you'll see that there's a link there. You can click on that and see the questions and answers that have been answered so far. All right, and this is very much the same as number 17. I think it's misnumbered here, but are there size limitations for the carrier or just the container interface?
And so, yeah, again, we are providing some results or some information there to help you with that. I think to Pat's point, the limitations on the overall size of the carrier we've defined somewhat in the theme, and the container interface we've also talked about in the theme. Um, and again, the sort of the default answer I'll provide is the same one we've talked about before here. Use your engineering judgment to make assumptions about the design and present that back to us because we're looking for ideas here. As you can tell, we don't have all of the answers figured out ourselves yet. We're looking for you to help us with those.
Thank you, Chris. Number 28, the original theme description has inconsistencies with the revised statement, and both have major inconsistencies with the NASA presentation link. Can we have one set of internally consistent requirements?
So, to clarify a few things there, the NASA presentation is there to give you context on what we're looking at and currently considering, but it's not there to be a requirements document on what you design. Again, we're looking for new designs that can have us look at this problem in a very different way. I'd also note that in looking at what's in the original theme description versus the update, the lander capacity is described in the original theme as being on the order of 1,800 kilograms. The total mass for your system design is constrained to 1,600.
Thank you so much, Chris. And that actually is the end of the highlighted questions for the SPLC theme. I'm going to actually ask Stacy Dees to join me for the programmatic and miscellaneous questions highlighted. And I'm going to go ahead and ask those questions and ask Stacy to answer them. So we really only have one question here to go over, and that is number 2. Given the expected diversity in the prototypes that each team may build, do you have any general guidelines, requirements, or constraints for the prototype?
So we actually don't on purpose have any real specific guidelines, requirements, or constraints for the prototype. That's really up for each team to decide what the best way for you to showcase either a full system if you've got something that you can demonstrate, or anything, a small component or subsystem of your architecture. The only thing that we do have some minor constraints is the availability of the size. For those who are selected as finalists, we will be doing a poster presentation, which would be a great place for you to, if you have any type of hardware that you want to show. And so to make sure that we have space for everybody, we're just asking if you're a finalist and you're selected to come present at the actual RASC-AL Forum in Cocoa Beach, that you would let us know in advance by the registration deadline if your prototype is going to be larger than about a 3-foot cube footprint, if you require access to an outlet so we can make sure we have power for you. And then most important is to allow us to be aware of any potential safety concerns, whether it's big or small. We just want to make sure that we are keeping everybody safe. So if you've got anything like pressurized containers, hazardous materials, or rechargeable batteries, things like that, just let us know so that we can make sure that we've gone through the proper safety channels and that it's okay to actually bring those together. So all of our finalists will be getting more information about that as we get closer to the deadline.
Thank you, Stacy. And I'll go ahead and mention this now as well to all of the people who've joined us on the call. If you are selected as a finalist and, oh, my lights just went off. If you're selected as a finalist and if your prototype is larger than a 3-foot cube or needs to be freighted to the hotel, you may want to consider that there will be some charges there for both shipping and to hold it at the hotel. So if you have any kind of budget in mind for that, you need to probably consider that now up front as you begin to develop and design and build your prototype. And that is actually all of the questions that we have for the programmatic and miscellaneous highlighted questions. At this time, we can go ahead and take any additional questions from anybody who's joined us here on the call. You can use the raise hand function if you'd like to unmute yourself and ask your question to our steering committee now. Also here on this page, we encourage you to scan the QR code here with your phone, and we've got a PDF document of the complete 2022 RASC-AL competition guidelines here for you. So if you're interested in looking over those again, we really encourage you to do that as you continue to work on your proposals. If you have got any future questions or any questions that don't get answered now, you can email them to the rascal@ninet.org email address, but we'll go ahead and answer any questions that we don't answer here from the chat. We'll go ahead and answer those and post them to the PDF that I sent out earlier today. That link won't change. The document will just update. And we'll send you all an email when that document has been updated, hopefully before the end of next week. So I'm going to go ahead and take a look at our participants list, and it looks like we already have a question from Dave Aiken. Dave, would you like to unmute yourself and ask a question?
Yeah, hi everybody. On the answer to question 17 on the Suport Logistics Carrier, you referred to the PDF document. The PDF document in term in several places says, this is explained by the attached graphic. There are no attached graphics. Is that going to be coming, or are we going to just have to use our imagination?
So, Dave, I will get those attached graphics. They are beautiful and wonderful, but a warning, I don't want people to take those graphics and say, oh, here's the design they want. What those graphics demonstrate is a concept for a functional operational capability to get logistics from point A to B. They are not to be interpreted as this is what we want to see you go design. We've already got people doing that. So yes, use those graphics to give you a sense of the functional needs and the constraints going through the system, but please do not feed back exactly what you see in the graphics.
Pat, have you ever known us to do what we're told?
Dave, no, never you, but others.
Okay, thank you.
Who let you go first?
I raised my hand first.
All right.
Alphabetical order.
So yes, I know the exact graphics you're talking about. That's part of the chain of data where some things get put in one place and the other things get put in other places. But I know what they are, and I'll get them for you because they've already been approved and given out to the world. So we shall do so.
Thank you, Pat, and thank you, Dave. We've got a question from the chat from Tara Vega for the Universal Sample Containment System theme. Should we account for wireless communication between the cooler and other devices, and if so, which type of communication would it use? Should the unit be able to communicate on its own, or can it communicate through existing communication systems on lunar rovers and other vehicles?
So I'll parrot Chris here. You tell us what assumptions we should take and why. Definitely, do you want to be able to somehow communicate with the integrity and the temperature? Certainly, I think that would be a good thing to do. We're not going to tell you how to do it. It could be Wi-Fi, it could be a plug, it could be Bluetooth. You tell us whether it should be on the rover or it's just going to be in the Orion or some other place. We want to hear from you what the right rationale is.
Thank you so much. And moving on, there's another question from Tara Vega for the Universal Sample Containment System theme. Should we consider locking mechanisms for individual sample containers or for the full containment system at all?
So I think this one and looking at the next one in the chat here that's also related to the theme about managing temperature and pressure and humidity. I think in both these cases, we're again looking for you to come up with what you think is right for your system in order to meet the needs of being able to transport a number of different samples for us and maintain their integrity.
Thank you, Chris. And that answers the next question that we have in the chat. We've got some questions here for the ISRU theme from Asim Qureshi. Do we have to develop systems for excavation if part of our ISRU system lies underground?
Yes, that would be in the scope of defining your entire system.
All right. From Asim Qureshi again. Does the entire ISRU system need to be in one piece, or can it be made in multiple deployable parts?
So it can be in multiple parts, and indeed one of the things we ask for in the landing or in the theme is to tell us how many landings you would need to get your system down. While we would generally prefer systems that could come down in a single landing rather than multiple, if what you're developing needs the multiple landings or it really provides some additional benefit by taking that multiple landings, we do want to hear about that too.
Thank you, Chris. We're moving back to the Universal Sample Containment System theme. Is it more important many samples in larger quantities or fewer samples in larger quantities?
So this one, I don't want to just completely punt back to the assumptions because I think there's room to look at what's been described in terms of NASA's goals for the Artemis missions, as well as NASA's goals on the planetary science side of things going to the moon that may give some indications of specifically what kinds of samples are being looked for, and that may help drive the answer to that question. So at least in this case, I'll point you to those places as particular places to look to help make up the decision of what kinds of samples and their quantity and size to go after.
Thank you, Chris. For the ISRU theme as well, what is defined as subsurface ice? Are hydrated materials within 1 to 0 meters on the surface included, or only subsurface ice sheets like a glacier?
So I thought about this one a little bit, and I don't want to constrain it to just one or the other because we expect we will encounter both depending on the locations we go to on Mars. So determine what your system can work with. If the system you design is able to handle both of those kinds of sources, that suggests that it's got a greater robustness to where it's deployed, but that may then have impacts on its ability to perform with respect to any one of those types of resource. But you don't have to design a system that covers both of those cases. You can pick one and focus on that.
Thank you, Chris. We're going to ask a question from the PUP theme. A key aspect of the portable utility pallet is mobility. It was mentioned that the PUP does not need to be self-mobile. Are you able to provide information on how PUP will be transported from point A to point B? Will it be a crane-like device, a forklift, etc.?
So I'll take that one.
Go for it.
So in our current architecture, we have two mobility systems. We have an unpressurized rover and we have a pressurized rover. Either one of those would be able to either carry or tow the pup to its new location. Or you could choose to put its own mobility system in the base of the pup. That's up to you. But you need to realize that towing on the moon is not like towing on asphalt. You probably, if you're going to tow it, you probably want it to have powered wheels anyway, such that you're not taxing the lunar terrain vehicle or the pressurized rover. The pressurized rover is big enough that if you configured the pup properly, you could actually hang it off the back and it could actually run it. That was an old NASA design, was actually to go do that. So you have options, but don't assume that if you just put a set of wheels on it that the rovers can carry it. That might, or can tow it. You might have to help. So think about it from that perspective.
Thank you, Pat. We're going to go ahead and take a question from someone who's raised their hand. Alan Debert, if you'd like to unmute yourself and ask your question now, it would be a great time.
Hi, I just had a quick question about the dates. So on one of the deadlines, it says June 20th to the 23rd. And then I look at what that link goes to, and it says July 20th to the 23rd. I just wanted clarification on those dates.
Yeah, so the 2022 RASC-AL Forum will occur in June 20th through the 23rd. So we'll go ahead and we'll update that.
It's on the hotel tab as well as the poster and stuff. That is July. So
thank you so much for that. We'll go ahead and fix that for you. And thank you for bringing that to our attention. Yeah, so the RASC-AL Forum will occur in June. So any of those July dates, those are a little too late. So we'll go ahead and move back to the chat. We have a question from Arturo Lopez Nava for the ISRU theme. Are we able to develop a working prototype for certain subsystems? For example, having the whole system virtually represented and then the drill and gas treatment be physically working and presented at the competition.
So I think that's an excellent approach to doing it. We don't want to bring to Cocoa Beach industrial scale ISU production facilities. That might be a little taxing both on the hotel and on your budget. So at the system level, just remember that you have to design the whole system. You can't just focus on one part of it. Yes, if you want to do a demonstration or a prototype of that one part, wonderful, but you need to show it how it all works together at the system level and answer the theme requirements and what we're looking for. So I think yes, just be careful not to focus on that solely.
Thank you, Pat. We have a question here from Brett Lauerhouse on the Mars ISRU theme. Is there any limit on the number of and/or scope of remote operators?
No, you could include as many as you like. Keep in mind that that does have a budgetary impact for you, and we're not putting you in a budgetary constraint, but we are asking you to assess the costs of your system, and that includes the operations cost.
Thank you, Chris. A question from Tara Vega again on the Universal Sample Containment System theme. What current sample collection system are you using? Can you share details?
Pat, I don't think we have anything that's a specifically prescribed system here, do we?
No, so what will be available will be a form of if you go back to Apollo and look at the EVA tools they basically had they don't like to bend over and pick up rocks, so they have a tool that they reach down and they grab it with. That's one way they'll be acquired. That's with humans. But the lunar terrain vehicle will be equipped with a small robotic arm, and we're hoping it will be collecting samples too. So that might be a different type of interface, and it might be, of course, it would have to take the sample to the sample containment system or carry it with it. So yeah, there'll be two modes. There'll be humans using basically what looks like a pooper scooper picking up the sample. That's what they look like. I'm sorry. And then the robotic arm picking it up in teleoperated mode from Earth or from the gateway.
Thank you, Pat. There's a question here from Aiden for the Universal Sample Containment System theme. Is the USCS going to sit stationary in one of the transport vehicles, Gateway, Orion, etc., or will it be required to be moved to the sample collection site where the sample is taken and stored, and then the whole system is moved back to the vehicle?
So you get to design that concept of operations as part of your system design. Certainly, it's going to need to at least make its way to the lunar surface in order to have samples loaded into it. But the degree to which it gets moved from an ascent vehicle out into the field back to an ascent vehicle, you get to define that and how that impacts your system and your operations.
Thank you, Chris. Here's a question from Nikki on the Mars ISRU theme. Should we consider the most recent planetary protection guidelines as fixed or assume a possible alternation in 20 years at the start of our mission, given the advancement in space law and the ISRU technologies being implemented at a greater rate? And I think this may have been answered already in the Q&A doc. Am I wrong?
Actually, I don't know if we had this one, so I'll go ahead and take the time to answer it here. So I don't think you need to treat them as fixed. I think there is the possibility for them to evolve moving forward. However, we would want to know what evolution do you see being necessary in order for your concept to work, because that will help give us a sense of, is this something that still fits within current guidelines, or will it require there to be some effort to shift those guidelines going forward?
Thank you, Chris. From Megan Gallagher for the ISRU theme, since we're assuming the location has been identified, what assumptions can we make about the subsurface ice sheets? For example, depth, amount of ice available, etc.
So similar to the discussion earlier about whether it's just hydrated materials in the regolith or an entire glacier there, you get to make those assumptions, but keep in mind that those assumptions and how they drive your system do then constrain how applicable your system is once we find out where these reserves really are. If your system only works for things that are immediately below the surface and are very pristine samples of ice, that may make it easier on your ISRU system design, but it also then constrains how many places on Mars it may then end up being applicable. So you get to make those assumptions, but keep in mind what impacts they have on how universal your system then is.
And those assumptions have to be based upon some facet of reality. We don't want you to assume there are giant piles of ice sitting there on the surface and all you got to do is surface. They have to represent, the current knowledge as you have research with respect to ice on Mars. You will not be looked upon fondly if you make assumptions that are not consistent with what we think is real.
Thank you, gentlemen. And I'm going to take this moment to encourage you, if you have any additional or follow-up questions, feel free to pop them into the chat or raise your hand using the built-in feature. We're going to move on to a question from Dave Aiken. For the SPLC theme, if a logistics shipment is split over a number of individual Suitport units, can we leave them on the lander and bring them to the habitat one at a time? Or do you want them to get all of them off of the lander at once?
Pat, do you have a preference here?
So again, that's part of the operational constructs. For example, if you're doing this all robotically and it's occurs over a period of weeks or months or whatever it is to transfer from point A to point B, you don't have to get them all at the same time. But it also goes into your lander assumptions. If your lander is going to, if it doesn't last more than a week after landing, well, then you maybe have to move those things quickly or time it with the arrival of the crew. So as we keep on saying, it's up to you. You need to establish your assumptions and justify them. So I can see either one of those being in the trade space, depending on a set of other assumptions in your concept of operations.
Thank you, Pat. We're going to ask a question from Arturo Lopez Nava on the ISRU theme. What assumptions can we make about the rate of ice/water extracted?
So this is, I think, part of what you're going to be designing in your system is knowing that, as we've talked about before, the assumptions you make about what resources are available and where they're located, you're then designing a system that will provide those, in the form of ice, in the form of water, in the form of vapor, whatever form you take, at a certain rate that depends on your design. So it's not so much about making assumptions there as that's one of the things that will come out of the design of your system.
Thank you, Chris. Now we have a question from Sarah on the Universal Sample Containment System theme. Do we need to design a sample extraction method at all? Or can we assume that we just receive the samples in a condition ready for storage?
It's the latter. You can assume that you're receiving samples and you're responsible for the storage.
All right, moving on to a question from Priyal Soni on the SPLC theme. Can you clarify the expected level of autonomy in getting the SPLC off of the lander to the rover and attached to the habitat?
So I think we've already answered this one. It's up to you to decide what level of autonomy you want to put into your design. Again, the current NASA concept has the crew doing everything, and we don't look upon that favorably. So the more automation, the better, unless it puts in extra cost and extra risk that are not acceptable. So you do the balancing act.
Thank you, Pat. And that's all of the questions that I'm currently seeing here in the chat, and I don't see any raised hands at the moment. I'm going to go ahead and put out a last call now as we go over one of our last slides here. If you've got a question, please feel free to pop that into the chat below or to raise your hand using the built-in WebEx feature. We'll go ahead and answer any remaining questions after we go over the next slide, which goes back to Alan Diebert's question about the upcoming dates and deadlines. So we've got a couple of important dates and deadlines that I'd like to go over here with everybody. March 1st, 2022, of course, is the deadline to submit your proposals and videos. All of these deadlines occur at 11:59 p.m., which is midnight East Coast time. So if you're not on East Coast time, go ahead and build in that extra couple of hours there. On March 28th, we'll be sending out selection status notifications to all of the team leads and advisors. So if you're interested in figuring out your selection status, it'll go to those individuals. Then our finalist teams are selected at that point, and the remaining green deadlines here below are only for finalist teams. So on May 15th is the deadline for online registration and payment. Also, this would be the deadline if your team has an extremely large or a possibly dangerous prototype. It's by this date, May 15th, that you'll need to email the RASC-AL at nianet.org email address with any additional requirements that your system might need. Just as a note, we might need to ask you not to bring certain parts of your prototype if they end up being especially dangerous for other people to be around. So just keep that in mind. Email us early if you guys have any questions about your prototype. The next deadline is, of course, May 30th, which is the deadline to submit your team's technical paper. And then the deadline to submit your team's poster and chart deck presentation will be June 19th, right before the forum. So your digital poster file will come to us and we'll put that up on the website. We'll also have your chart deck files with us, and we'll be using our version of your submitted chart deck files during the on-site forum. So just keep that in mind. We won't be accepting any additional presentations on PowerPoints. We won't be connecting your computer. We'll be using the one that you already submitted. It'll be loaded onto the presentation laptop, and you'll have a clicker that will be able to go through the slides like that. And then finally, June 20th through 23rd, 2022, next year, is the 2022 RASC-AL Competition Forum. And we look forward to seeing all of our finalist selected teams there on site in Cocoa Beach, Florida for the first time in 2-3 years. So we're really looking forward to that. And yeah. So it looks like we've got a question now from Arturo Lopez Nava. If you'd like to unmute yourself or show your face, we welcome you to do that now and ask your question. Arturo?
Yes, my camera is getting connected. So I have a quick question. So I was looking into, this is for the ISRU, for the cryogenic storages. I know there's some prototyping going on at NASA with Boeing today, as of today. Can we assume our system using that, or how can we, I guess, assume correctly if that's going to be available for my technology? For example, there's some they're using ceramics and they're testing, and can we assume their statistical data is going to be available for us by that time, or how can we go about that theoretical storage if that's already being developed, or what are the assumptions we can make?
Yeah, I definitely think for systems that are currently being, or technologies that are being, developed right now, especially where there's information about those, making reasonable assumptions about that being available down the road is definitely in bounds.
Perfect. And then if it's something material wise that is not disclosed to us, how can we I guess present it? Can we say, hey, this is something in your department, y'all have? And I mean they say, very few things. Obviously, I understand it's, very, top secret. How can we explain it? Do we not have to explain it thoroughly? Can we just say this is what we're going to use, these are the specs, and leave it at that?
So yeah, in that case, I would say take the information that is available, use engineering judgment to then make reasonable extrapolations from that, and again, describe the reasons why you made that assumption. So, maybe you can say, okay, based on the trends here, we think it's going to be able to perform at this certain level, require this kind of power, et cetera, going forward, and use your judgment. The judges will use their judgment to then decide if that seems like a reasonable assumption or too optimistic, or for that matter, too pessimistic.
Sounds good. Thank you, sir.
Mm-hmm.
Thank you, Arturo, and thank you, Chris. I'm not seeing any additional questions that have been popped into the chat, and I'm not seeing any other raised hands. So we'll go ahead and just stick around for maybe another minute or two to answer any last-minute questions that might come in. But I do want to say thank you so much to everybody for joining us here today. We will be getting all of the questions received on the call. We'll be transcribing the answers that Chris and Pat have provided over the past hour, and those will all be added to the PDF that I sent out earlier today. You won't have a different link. It'll actually be at that exact same link. We're going to update that document, and we'll let you guys all know when we've got that updated and transcribed, and send you an email. But you can hope to look for that before the end of next week. It looks like we've got one more question that's come in from Ruben Isaac. ISRU, is there a preference for a virtual prototype that covers the entire system rather than a physical prototype for a component?
If I had to guess, I would personally be more interested in seeing that virtual prototype of the entire system, but not to say that there's not something really valuable that could come from a physical prototype of a single component.
Thank you, Chris. And we've got a general question here that I'll ask Stacy Dees to answer. Do we know how many teams will be competing and how many will be selected?
So we get asked this question every year, and unfortunately, we don't actually publish how many teams propose or submit NOIs, but it usually is fairly competitive. So you do need to know that there's definitely going to be some competition there. And we have funding to select between about 15 and 16 teams. So it could be up to that. But of course, we only bring teams in if it merits. So if only 10 teams merited being in the competition, then we'd only select 10. But it'll be about a maximum of 15 to 16.
Thank you, Stacy. And at this time, it looks like there are no additional questions that we've received from the chat and no other raised hands. So unless anybody here on the line has something to say, Stacy, Chris, Shelly, Pat, I want to thank you guys for joining us today and give you the best of luck working on your proposals over the next couple of months. We really look forward to seeing what you guys come up with, and we're looking forward to that March deadline. So thank you again for joining us today, and we will hear from you then.